right. Yeah, good morning, everyone. Very happy to be here. Thank you, Marco, for inviting us. For me, this is actually the first in-person conference in 2 years, so with the lockdown and all. So it's just, yeah, really nice to be doing something like this again. Yeah, so today we're going to be talking about Ghidra2cpg, and so this is all about creating graph queries that you can use to find vulnerabilities in binary code. And yeah, I'm presenting today with Claudio, who's here, and Nico, who also works at our company. He unfortunately is not here today, but he did a lot of work on this as well. So I would just like to mention that. Yeah, a few words about us and about this talk. So in our day jobs, as Marco already said, we work at a startup, and we're building automatic vulnerability discovery. So we're in static analysis, meaning we actually write programs to look for bugs in other programs. That's essentially what we do. And the content that you're going to be seeing today is kind of a combination of what we do at our work, but also just a hobby project. And this was a hobby project that Claudio started. He thought that it would be really fun to take apart some routers that you would find, like consumer-grade routers, stuff that you would find at home. And so we took a look at the D-Link routers, and it turned out to be a pretty juicy target. So there's a lot of stuff in there, and you'll see a lot of that stuff as well today. Yeah, and it was just a great opportunity to test out whether our stuff really works, and of course finding out where it does not work so that we can go ahead and improve that. And so today, I mean, this is a talk mostly about methodology. How would you approach such a target? But we'll actually also look deeply into the bugs that we found, as well as into how we exploited them. So overall, everything that you're seeing today, I mean, this is not commercial stuff. This is open source. You can download all of this and you can play with it. This is very important to us. So it is, from a technological point of view, something that we also use in products. But yeah, we have a huge part of it that we make available to the community. And the platform is called Joern, on Joern.io. And the idea is to create a bug hunter's workbench over time. So something that you can use during your code audit that will support you in reading your code, and that will also support you in creating exploits for it. This is actually a quite old project at this point. It started off in 2013. It was just me at that point. And yeah, it was mainly for research. And the initial idea was to create a fuzzy parser. So that's a parser that's like very robust. Regardless of whether you have a build environment or not, it will somehow translate into syntax trees, and from there on to control flow graphs and so on. Because I was doing research on like pattern recognition for vulnerability discovery. And so in that setting, you can't go ahead and configure build environments for like 1,000 Debian packages or something like that, to get your experiments running. So you need something that's a bit more robust. And initially, it was that fuzzy parser. Today, it's become more of an interactive programming shell for vulnerability discovery. So you import code, still with robust parsers, then it's available in a graph database, and you have a query language that you can use to then explore your code. It's based on Scala. I realize that's not very popular in the vulnerability research community, but it's actually a very pretty language. I hope you will agree after the talk. And we do have the ability to script this with Python as well at this point. But yeah, Scala's cool. Just want to say that. Anyway, at this point, we can not only analyze C and C++, but also Java, JavaScript. And then at some point, we went more towards bytecode analysis, so JVM bytecode and LLVM bitcode. Yeah, and eventually binary, which is what we're speaking about today. There's a query collection that you can check out, just a bunch of queries to get you started. So that kind of turns that whole thing into an automated scanner. But I just want to say, I mean, we're not really about, at least in this open source project, we're not about building this scanner that just gives you the bugs and that's that. It's more about building a code exploration platform, something that you can actually use during your audits, more in the style of, let's say, IDA or Ghidra or something like that, and less in the style of a linter or automatic scanner. All right, so it works pretty well on source code. We've seen that in the past, so here's one of those typical queries. Here we look for an allocation, and inside that allocation we perform arithmetic. Then we look for a memcopy, and we check that that allocated buffer actually goes into the first argument of that memcopy. And then we make sure that there's there is something in the amount that we copy that's not equal to that arithmetic expression. And so that is something that leads to heap-based buffer overflows a lot. And we used this query in 2014, found a buffer overflow in the automatic updater of VLC. Used the query again in 2020 and found another one, right? Same code more or less. Different instance, but you can see you can kind of generalize there and have a query ready that you can fire years later and it will return bugs again. And so then the question is, what do we do if all we have is binary? And we've looked at that question before. So if you've followed our work over the past years, there used to be what's called Joern, so binary Joern. That was based on R2. But the experience was not comparable to what you have with source code. Essentially what we did there was we imported the disassembly and then started writing queries and realized, oh wow, this is actually not, you can't just take something for source code and then import a binary and expect similar kinds of results. And so the main learnings for us at that point were that, well, it's hard to adapt these approaches to binary, it's not trivial, and the other thing is that we actually spent quite a bit of time before we realized that. So it's actually better if you have if you have a target available, and while you're building this, you're already trying it out. Just a few words about how source code in binary is different. So in source code, often you have a vulnerability, like a good candidate point that already concentrates itself in a single statement. Like for example, if you have a string copy here, strn copy, and you see that, okay, they're actually using the length of the source buffer for the copy operation, that's already pretty indicative of a buffer overflow. Sure, you want to make sure that you do some data flow analysis to actually ensure that you can get to that point, stuff like that, but that's already very indicative. Or for example, this typical malloc bug width times height, where you have an integer overflow that then leads to a heap-based buffer overflow. Or like a truncation here where somebody says int len and then assigns string len to that variable. And so syntax trees are already quite powerful to describe that, and then you can do a data flow analysis to kind of narrow in on that. All right. For binary, you have a call site and you see, okay, something's being called, and then it tells you, well, the arguments are A1, A2, and A3, and you're like, okay, thanks, Sherlock. This is not very useful for us, is it? So reconstructing these arguments is crucial. Another problem is that you don't really have variables anymore. Like variables are actually, the programmer's telling you what he's doing with that memory location. That's not the case in binary. All you have is memory locations and registers. And so a huge part of what you need to do is recover these high-level variables. There's a good paper about that where they call that abstract locations. I just put it here on the slides. You can check that out later if you like. And the good thing is what changed between 2016 and now is Ghidra was released. And Ghidra just has, apart from having a good disassembler, it has an amazing decompiler, and decompilation actually deals with these topics that I just talked about. It does approximation of local variables, intra-procedural recovery of arguments, so within a function, and even recovers some control structures. And so the idea was, why don't we not just make available the disassembly? I mean, that's good, but why don't we just use the decompiled code and feed it into our robust parser? I mean, we have that parser, right? So let's try that. And that actually turned out to be a really good step to take. So Ghidra2cpg extends Joern. It imports the disassemblies. You can also import the decompiled code. We do both today. And what you end up having is a polynomial time interprocedural data flow analysis for a binary, which with Ghidra you don't really have. You have an intra-procedural reaching definition analysis with Ghidra, and that's that. It's still highly under development, but we're developing out in the open, so you can check it out. And now, yeah, for our target.
So this was the first time I started doing IoT security, so I didn't know exactly what I was doing, almost at all. But I tried to go ahead and pick something that is interesting. The way these targets were chosen were basically just like go to a major router manufacturer website and see which products are on the main page and pick one that is like more expensive, on the expensive side, like around $100, $120, and one that is more mid-range. So maybe not something that your grandma would buy, but you know, your sister maybe or something. And the other consideration was whether the firmwares were encrypted or not from the get-go. And in this case, they were both encrypted, so that means that not a lot of security researchers looked at it as much as for firmwares that aren't. So these are the two targets, the DRX1860 and the DR842V2. And they are both release date 2021, so they're fairly recent, still on the market, still on the web page of the provider. And after the targets were chosen, and if you want to do something like this yourself, basically you have to purchase a couple of tools. So for example, here you see a voltmeter and a UART converter, an analyzer for this, and a couple of wires. And basically, when you have all of that, you're ready to go. All of the tools cost around $100, $120, or if you don't want to spend the money, you can just go to your local hackerspace, and they usually have all of this. For example, in Berlin, it's C-Base. They have all of this on, and you can use it for free. So after all of that is done, what you have to do is to solder the stuff. You solder a couple of 3 wires, in this case, in one of the router, in the UART port of the router, and you solder 3 wires in the connector, and then you connect them both, and then you're ready to go. If you're as bad as soldering as I am, you can also go to your local provider of like a computer repair shop, and they can do this for you for very cheaply. This is Berkay from Berlin, from Computer Handy Shop. He's watching right now. Hello, Berkay. And he did a wonderful soldering job, much better than the one I could do. And just to see how it looks like when your soldering job is very poor, these are on the bottom there, you see all those glitch jars. And those are the things that you see when either the wires are bad or you set the incorrect baud rate on the connection. Yeah, so this is the whole setup. You have the UART connection, like with a good UART connection in place. You have you can just connect via screen, and then you get, in most of the cases, you get a root shell. Not in all of the cases, like some of the newer devices have like some protection mechanisms or a password in place, but you can get around that usually pretty quickly with some tricks in U-boot or yeah, just like trying stuff out. So when you have all of this and you have a root shell, basically what you do is you just go in and you try to understand the system a little bit, how it works. Obviously, the first thing that you want to do is just to look at how is the web interface shown, right? How that when you go to the admin panel of the router, what is the thing that is serving that traffic? And here it's just basically there's in one of the targets there's like one old school CGI program, UHDPD, and basically has a couple of Lua scripts as a configuration and which point to 2 binaries, like in one of the devices, and one of the binaries is used just one time in the HTML of the admin interface, which means that that's probably an abandoned library or a binary that has been forgotten there. So that makes it a much more interesting target and a target to look at. So now you have the binary, you have one of the interesting binaries. Then in my case, I just started Ghidra and the Joern shell at the same time and started to look into the target a little bit more closely.
All right. So yeah, the first thing that you want to do is you want to kind of map out the attack surface. So what's the code that actually needs to deal with the data that I can provide as an attacker? And you'll see a query in a moment, but let's be honest here, there's a lot of tools that you can use to do that. You essentially want to look at the external functions. So what are the library functions that are being called? And so we did that for the two binaries, so for the two different devices. The first binary was called MTFWU, that's from that more expensive router. And it uses libc, like very rawly, to do string handling, file operations, and memory allocations. So that's nice. I mean, there can be memory corruption in that, and it's a web application. Don't forget that. For HTTP, it is very old school. It uses getenv, so environment variables, to get the HTTP request data. So extremely old school stuff. Then for the other one, this is actually the cheaper router, but it's not as old school. So these guys also use libc functions for string handling, file operations, memory allocation. But then they have a library called Mongoose that they use for HTTP, well, for all handling of HTTP, really, including WebSockets. Then they have a JSON library called Jansen. We didn't really look into that much. And there's an internal RPC library called DJRPC API. We also didn't look into that too much. You'll see we didn't have to look very deep, actually. So I'll just talk about that cheaper router for now, and then Claudio will talk about the more expensive one. So for the cheap router, we just talked about how it gets all of its HTTP data via Mongoose, and Mongoose functions all start with mg underscore. So the first thing that you can do is kind of like list all of the different calls to mg functions, just to get an idea of how do they receive attacker-controlled data. And here you see there's a function called getHeader, which, as the name would imply, gets some data from an HTTP header. Then you have getCookie that gets stuff from cookies, pretty standard stuff. And then what you can do is, you can dump out all of the decompilations, all of the decompiled functions of methods that call one of those mg functions. And you can just dump that to a file. That's pretty nice. That means you can scroll through it and you actually get a good idea, of like the first responders in the HTTP chain, right? And then as you try to automate this, you can just mark all of these functions to then use them later. So here's a query that we use that essentially says, take all the calls to mg functions and go to the methods that they're in. And then just start walking the calls, the outgoing calls, and only take the internal ones and do that 10 times. So you're just kind of expanding into the code and along the call graph, and you're just marking this. You're saying, okay, this is attack surface, right? So with all queries that we show now, we're just going to filter to only look at these functions. So you're not looking at the entire binary, you're looking at the functions that have something to do with the HTTP handling, directly or indirectly. And so here was our first query, really, and it's super simple, and the fact that we found something with this is a bit problematic. So the only thing we do here is we say, okay, look at string copies, strn copies, and mem copies. And then look at the amounts here, all right? The amounts are in the third argument. And they should not be literals. It should not be a constant amount that we're copying, because otherwise, there's probably no buffer overflow in that, right? And then look at the first argument. That's the destination of the copy operation. And it should be a stack buffer, right? So stack buffer, constant size, but a non-constant amount that we copy into it. And the last thing is just, it should be part of the attack surface, right? Which we marked with the previous query. And that's it. And so you can already see the ability to inspect arguments here is really important. Otherwise, you could not do this thing here. Now, the nice thing about this query is this is exactly the kind of query that we would run on source code, right? The only thing that's a bit different here, which we would need to clean up to have the exact same query, is that thing here with a stack. Because here we're saying, okay, yeah, Ghidra has nicely marked this as a stack buffer. So here we would really need to say it's a local variable that is an array and stuff like that. And so this is just shorter, but this is the only thing that keeps you from running this thing on source code as well. So exactly the same query. Yeah, and so we ran that, and yeah, there was immediately a buffer overflow that we found. So this is in the WebSocket data handler. And you can see here, they're looking at the packet. It's called param3. And if it starts with an init, then they're going to go into this block here. And then they take the rest of the packet, and they just copy it into a stack buffer. And they really don't mind how big it is. This is the amount that they copy. So yeah, you just overwrite it. And the nice thing on this device is also that, I mean, from an attacker's point of view, is they don't have any stack cookies or canaries or anything like that. So you really just overwrite the return address and can, start exploiting this. Yeah, there were really just two results, right? And this is the second one. And this is in a code that is in a callee of WebSocket data handler. So also a function that you can reach with your WebSocket packet. And here's the second buffer overflow. It's also extremely simple, right? You have a stack buffer. Here's what you control. Here's the size of that. And there you go, another exploitable bug, right? Yeah. I talked about how we have the disassembly, so that's pretty nice. What we could now do is extract gadgets for our exploit. Because what is a gadget, right? A gadget is really just a sequence of instructions that ends with a red, right? And so we could say, okay, give me all of the, walk backwards through the control flow graph, like 5 times in this case. And just dump that to a file again. So that gave us gadgets that we could use. And we selected a few. And you can put all this stuff in scripts. And then, there are Joern scripts, which are just Scala scripts, really. And you can then reuse that every time that you want to dump gadgets. And this works across platforms as well, because we map return from different platforms to the same intermediate representation. And you can also write binary exploits in Scala if you want to, right? So here's my binary exploit in Scala. It contains 3 gadgets. It's not a lot of magic that we need to do. Fix the GP, make sure that A0 points to somewhere that we control, and then call popen, right? And you can see here, I'm actually passing in a shell command, which is just echo the string owned into tmp-lal. And that's what we used as a proof of concept to show that we can actually write an arbitrary file on the device as root. And then we send that over via WebSocket, and that's that. This is a 100% stable exploit, luckily, because they map the ANWeb base image at a fixed address every time. It's a remote root exploit because that ANWeb thing, that web interface, runs as a root. It's pretty much everything that you want as an attacker, right? You can do whatever you like. That's that, but that was really simple if you think about it, right? I mean, we didn't even need data flow analysis, which is a bit of a pity. So we looked for more, right? So we then looked for typical directory traversals. And so we were looking at fopen calls, and somewhere on the way in the data flow, we want to make sure that there's a string cat, so a concatenation. that's pretty indicative. Usually means, okay, they're just putting strings together and you can specify dot dot slash and break out, right? And of course, again, in the attack surface. Also 2 hits, both of them are directory traversals. But that was not all. Actually, when we tried to exploit this, we realized there's another bug in this. And we wanted a directory traversal, but we got more like a heartbleed style bug, which which is really funny, actually. So here's the code for that. I'll try to speed up a bit. So this is the function concat endpoint. It's a function that just reads an arbitrary file off of the device, and on each line is another file name. And then it will read all those files and put them together and send them back, right? And you have directory traversals in both of those file opens. Now, the funny thing is actually that, as they try to write that file back, they will call fopen here, and if you specify a binary to read files from, like these lines, then very often you'll get back an empty line. So then this thing here, fopen, by the way, if you call that on a directory, then this actually succeeds. You get back a pointer, you just can't do much with it, right? And then there's an fread operation here that they call on that. And the fread, they're not checking for the return value, right? So this fread will fail, which means this buffer here, ptr, which is just some pointer onto the heap, it will be uninitialized. And then they just write that back to us, right? So that's what it looks like. You just say dot dot slash, and so on, bin ls, right? And then you get back memory. And you run it again, and you get back different memory, right? So typical heartbleed style kind of bug. All right, and then Claudio?
Yeah, so for my bug, this was, it was, to be honest, it was a little bit disappointing, the bug that I found. So I definitely wanted to have a bug in my hand that has high impact. And I searched for a lot, and just because I've just started up, I wasn't really sure how to do it, where to do it, and so there was a lot of trial and error involved. But at some point, I just stumbled upon this bug, and I talked to a couple of people about it, and they were like, "Okay, this could be pretty bad." And also, I found out that this is the kind of bug that router manufacturers have had problems with for a very long time, and it was very surprising that this is still going on, like hard-coded credentials. So what's the bug? Here, the MTFWU binary of that more expensive device is getting, this is the Ghidra decompiler output, right? So this is how I started, and afterwards I'm going to show the query. So the getenv parameters here, calls, receive data from the outside, and specifically 3 getenv values are important: HTTP cookie, HTTP act, and HTTP auth here. If you look inside this function, this is the main function, you see at some point there is this string fw upload, which looks like firmware upload, so it could be something with the firmware. And here we see another string size of firmware is too large, so that's very probably, okay, it's a firmware upload mechanism inside the admin web interface. And if we look further down here, further up, we see that the ivar5 controls this call, right? So ivar5 comes from the 88f0 function, so the return value of 88f0. And this 88f0, so it should be some kind of authentication mechanism, right? And the funny thing is it takes 3 variables here. It takes PCVAR3, which is the cookie, and I've checked the cookie was indeed some kind of a authentication mechanism by just checking the web requests that were being sent from the admin interface. But also these two, which were a little bit fishy because we already have an authentication mechanism. And why is it another auth, right? So why is there a second getenv here, right? And also, the even weirder thing was this act here. And this act is actually the variable that is being string compared over here. So we have this action string that goes inside the authentication mechanism. So that doesn't make any sense, right? So let's look at the authentication function here, 88F0. Inside of it, there are three interesting things. So first of all, we see that the first parameter here is only checked that it starts with the string UID equals. And the first parameter of this FF88F0 is PCVAR3, and PCVAR3 is the HTTP cookie, and the HTTP cookie is exactly the value that is being used for normal authentication. But in this case, it's only checked that it starts with the string UID equals. So that's a bit weird. And looking further down in the function, we see another very weird thing is that the return value of this authentication function, which controls the firmware update mechanism, is taking the value from string compare of its second parameter with this stack buffer. And the second parameter, PCVAR2, was this auth string. And this auth string is compared with this stack buffer, which is also a little bit weird. And the stack buffer is just one line further up. This is passed into another function, 84B4, together with parameter 3. And parameter 3 is PCVAR1 act, so the action mechanisms. So this is very, very weird. And if we look in 84B4 a little bit closer, we see there's a lot of things going on here, but we see mostly that we have this sprintf call to the third parameter, which means, and this sprintf call has a format string with a hex value. So it spits out a hex value of PBVAR3. So that means that somehow this parameter 3 is transformed through to a hex value of PBVAR3, parameter 3 from PBVAR3. So this means that the actual, the HTTP cookie value that is usually used for authentication is completely ignored, and instead the authentication of the firmware is basically a transformation, a hex. Let's say it could be MD5. We could replace this function with MD5, whatever, of the other parameter act. So actually, it means that if you pass in a value for a random value for HTTP cookie that starts with UID equals and a hash value of HTTP act that equals the HTTP auth, then you can upload, replace the firmware of the device. So this is not like a typical hard-coded credentials vulnerability where you just like string compare two things, or where there's an actual string in the binary, but it's a little bit more hidden inside the code. Okay, so let me show you the query. So this is just like a step-by-step guide how to build a query. The first one is just like you import the code, you import the binary. After you have the binary, you can look in the graph and you can see all these assembly instructions, because now we're at the binary level. But we don't want the assembly, so we just take all the method nodes of the graph of the binary, which contains the Ghidra's decompiler output, and we concat them to a large string with new lines. And we import that, we create a C source-based graph from that string. So now we can run good data flow queries on it. So now this is how it looks like, right? So we don't have the assembly instructions anymore. Now we see the actual code of the Ghidra decompiler output. The same thing that Fabs showed, the attack surface tags can be stored with like this type of command so that it's easier later to reach those nodes. This is, for example, what you can do. If you've tagged the attack surface, you can just like list all calls in the whole binary, because you don't want to look like all over the code, right? You can just like do this, and then you know exactly all the specific places where data comes in. And but now we want to write the actual query. And the way I did it, I mean, you can do it like any way you want, but the way I did it was just to start at the heart of the problem, which was the sprintf call to the third parameter. So what you can just do is give me all nodes of sprintf, where the second argument is a literal that has this x, that matches this regex, which is the hex transform. So it basically takes the source parameter and it makes a hex transformation to the destination parameter, right? So this is sprintf transform, which matches this one line. For the second line, we want the 84b4 function, right, which actually calls sprintf, right? So we want that function to be passed to be identified by the query. And in this case, we just write sprintf transform. So this is the method that we just found, and we take all of the methods that contains sprintf transforms, and then we run two data float queries to see if those methods actually reach the sprintf. So, and in this specific case, you can see sprintf, this is that call over here, and then we check if one of the parameters reaches the source and one of the parameters reaches the destination of the method sprintf. And we call this parameter hex transform. This is all made up names. It's just like easier to remember, at least in my case. So we have parameter hex transform is the 84b4 function. And we go back to our bug, we remember that the 84b4 function was the fishy function that was that transformed the stack buffer here, right? So we have the parameter hex transform is the 84b4 function. So, and we want to take all the callers of this function, and we want to see if there is a string compare from one of it, if there is a data flow from the parameter of this caller to the string compare. And also if there is, if that same function that calls the parameter hex transform also has a data flow to the parameter hex transform. So then you have both of them together, and this can be improved a little bit, but and I mean it's good enough to detect this bug. So then we have the compare transform, and then the only thing we have to say is that, okay, is there a data flow from the attack surface, from the getenv calls to this function, and indeed we find that. And this is the whole query, how it looks like. When you run it, you get this output, so you get these three environment variables, and obviously the next step would be to actually confirm the bug. And you can do it in many ways. The way I did was just with LD preload, where you can just write a custom version of string compare, in this case, that prints out the strings that are compared. And then you just run this on one of the acts, which is get device info, and you get the hard-coded credentials for that specific action that gives you the device information. And then you can do the same with firmware upload and firmware update, and then you get the hard-coded credentials for those, instead of going inside the function and trying to figure out what's going on in all those bitwise operators and whatever. And this is all good, but you know, it's not super interesting because it's a LAN-based vulnerability, so you know, it's like kind of hard to exploit. But it would be interesting if we were also remotely exploitable, right? So a colleague of mine, Bernhard, suggested I should try a DNS rebinding attack, to combine this with the DNS rebinding attack. So this is very easy to do. Also, it was my first time doing it, but I highly recommend you try it out. You can just use the Singularity from NCC Group, this tool, where you can just spin up an AWS instance. You install the Singularity server. It's very easy. It's like in 5 minutes. You open, you know, the firewall ports on the AWS instance, and you have to do a couple of configurations. You buy a domain name, and then you can just trigger a DNS rebinding attack. And what's going on over here is that this grandma's secret recipe, this was on my local computer, and the browser should actually protect against this, right? Should actually protect against this type of thing. So you cannot just like go to a web page and the web page can request stuff from your local machine, right? So this is what CORS protects against. But if you manage a DNS rebinding attack, which works like you open a web page and the web page gives back a DNS response with a very short time to live. And the next time the browser request, or the web page that the customer already shows, the next time the request goes out, the DNS response is to a local address. And then with that, you can actually show a web page to a person, and then you can send HTTP requests to any local IP address of the local network, for example, the router. So to combine this with the bug, we can just show a web page to anyone and with this router, and then we can exchange the firmware on the fly, which means it's botnet ready.
All right, I'm just going to wrap this up now. So notes on disclosure, we did contact the vendor over 90 days ago in August, gave them an initial bug. They said that they would forward this to their R&D team and they would contact us, but they never really got back to us. So we contacted them again like very early in November because we wanted to talk about this, and we said, hey, you know, what happened to our bug? And also here is another bug, you know, if you like, but no response. So yeah, I mean, I'm hoping that, I mean, maybe they'll see the talk, maybe they'll fix it, maybe not. But you know, we tried, we really tried. So just want to say that. So to conclude, yeah, it's really nice to make a disassembly available in a graph database to then query it. But where it gets really powerful is if you have something that's a bit more high level, something that you would get from a decompiler. And that's what we're using as our baseline now. And it's just amazing how, even though this is actually from a binary, it's sufficiently C-ish to use the exact same queries. Yeah, you saw two types of querying. One is like, okay, I'm going to write about something that I think is going to be broken in a particular way, and then just get out the bugs. And then what Claudio showed you is he had something that he wanted to characterize across devices, kind of create a very complex signature that generalizes enough to use this across devices. And those are like the two use cases that you can go with those kinds of queries. And the reason we do this on binary really is that the parser that we have in Joern is extremely robust, meaning you can feed it anything that kind of looks like C and it will do its best job to create abstract syntax trees and control flow graphs and these kinds of things. So it is really a parser designed for hackers. If some code fell off a truck, you don't need to start configuring a build environment because you can't, right? You can use this on whatever code that you have, and the decompiler output from Ghidra compared to code that just fell off a truck is actually quite tame. Oh yeah, and finally, I guess, yeah, it's quite scary, certain consumer-grade routers. They're remarkably insecure. We didn't have to try very hard. Thank you.